Bismillahirrahmanirrahim. Assalam O Alikum. Dear student, welcome to my YouTube channel Learn with Azam. Today we will start new syllabus National Book Foundation Physics SSC2 Unit number 10 Simple Harmonic Motions and Wave. SLO base according to FBISC requirement question. Today we will solve the comprehensive questions, question number 1 to 5. Now in part 1 we can solve question number 1 to 5. In question number 1 of the comprehensive question, what do you mean by oscillation? Define simple harmonic motion and what are the conditions of our body to perform simple harmonic motion. Give examples of the body which perform simple harmonic motion. Here, first of all, understand the question. In this question, requirement is what is meant by oscillation motion and also define the simple harmonic motion and write the conditions of simple harmonic motion, then write the examples to perform a simple harmonic motion. First of all, what is meant by oscillation? An object is said to be vibrating or oscillating if it moves back and forth about its fixed position. Called the mean position, many objects vibrate or oscillate mass attached to a spring, a tuning fork, a pendulum, beating of heart, and the stringing of guitar or piano. Vehicles oscillate up and down when they hit a bump. Buildings and bridges vibrate during an earthquake. Oscillatory motion is a great importance because it is so common in our everyday life and occurs in many areas of physics. Here we have mechanical oscillations or vibrating are fully described on the basis of Newton's mechanics. Now, in simple harmonic motion, a special kind of oscillating motion is called simple harmonic motion. Now, in simple harmonic motion occurs when the net force is directly proportional to the displacement from the mean position and always directed toward the mean position. Also, we can define, in other words, when an object oscillates about a fixed position, mean position, such as that is oscillation is directly proportional to its displacement from the mean position and it is always directed toward the mean position. Its motion is called a simple harmonic motion. Simple harmonic motion denoted by SHM. Simple harmonic motion is the type of vibratory motion in which the acceleration is directly proportional to the displacement from the equilibrium position and always directed toward the mean position or equilibrium position. So we have explanation. If A is the acceleration of a body and x represents the displacement of a body from its mean position, then condition for the simple harmonic motion. The characteristics of simple harmonic motion as follows. In simple harmonic motion, a body oscillates about its mean position O and a restoring force is always directed toward the mean position O. The acceleration is produced by it is also directed toward the mean position. And third point, its acceleration is directly proportional to its displacement from the mean position. So we can see in this diagram here shows the simple harmonic motion. Now we can say that any system that represents its motion to and fro about its mean position or a rest position executes simple harmonic motion. Here some examples: simple pendulum, mass spring system, a steel ruler, or a free for displays sideways, a steel ball rolling in a covered dish, or swimming. In this diagram, you can see that this perform a simple harmonic motion. Simple harmonic motion oscillating spring without damping. So this damping shows the waveform and also perform a simple harmonic motion about mean position to extreme position and extreme position to mean position. Clearly we can see that in this diagram and rotation of a body. Thus, to get the simple harmonic motion of a body displaced from its mean position and then released, the body oscillates due to the restoring force. Under the condition of restoring force, the body oscillates and overshoots the rest position due to inertia. The restoring force then pulls it back, so the restoring force is always directed toward the mean position, and so acceleration is also directed toward the mean position or rest position. We can clearly see by this diagram. So question number 1, complete the answer and shows by diagram. So in this part, in next question, question number 2, we can see that show that the vibrating mass spring system perform a simple harmonic motion. What is the time period and one factor affecting on it? So first of all, see the diagram. In this diagram, we can see that body is shown in a mass spring system. Mass spring system body move from its mean position O to maximum position toward the right side and left side. So this is performing due to the restoring force. Now write the answer. Mass spring system. Consider a block of mass M attached to the one end of a elastic string, which can move freely on frictionless horizontal surface. Show in this figure and we can explain also. Explanation: when the block is placed, the elastic restoring force pull the block toward the equilibrium position. For an ideal spring, obey the Hooke's law, and Hooke's law is that elastic restoring force is directly proportional to its displacement from its equilibrium position. We can write that F is directly proportional to minus x. Here, negative sign shows the elastic restoring force, mean restoring force. So, F is directly proportional to its displacement and always directed toward the mean position. So, we have write that since F and X always have opposite direction, therefore we have negative sign in the equation. Each spring is a different, so the force is required to deform it. the softness of the spring or the spring constant is represented by the letter K. So the equation of Hooke's law F is equal to minus Kx. When proportionality sign can be removed, we can use the constant. So here we can use the constant K. Then according to the Hooke's law, F is equal to minus Kx. This is called the equation number 1. Now the motion of mass attached to a simple harmonic motion due to the restoring force produce the acceleration in a body. So according to the Newton's second law of motion, then second law of motion states that F is equal to ma. Here we can call the second equation. Now comparing equation 1 and equation 2, then we compare equation 1 and equation 2. Here left hand side are equal, so right hand side are also equal. Then we have ma is equal to minus kx. Here m is multiply, on other side it will be divide. So A is equal to minus K over mx. Here K and m are constant. So we have as a spring constant K and mass m is does not change during the oscillation of a mass attached to a spring. Therefore, they are constants, then A is directly proportional to minus x. So this equation is satisfied. Acceleration is directly proportional to its displacement and it is always directed toward the mean position. Here negative sign shows that acceleration of a body is always directed toward the mean position. So A is directly proportional to minus x. If the restoring force obeys the Hooke's law, then we have oscillatory motion of a mass attached to a spring, that is called a simple harmonic motion. Then we have the time period for a mass spring system. So we can calculate the time period of a mass spring system. Then we using the constant here, since acceleration in a simple harmonic motion A is equal to minus constant multiplied by x. Then we use the constant here omega square. Then acceleration A is equal to minus omega square multiplied by x. Then we also know that omega is equal to 2 pi over t. Then omega square is equal to 4 pi square divided by t square. Now putting the value of omega in above equation, then A is equal to minus 4 pi square upon t square multiplied by x. So the acceleration A is equal to minus 4 pi square x divided by t square. Then we have from the above equation acceleration is equal to minus k over mx. Now comparing the both equation, then left hand side is equal, so right hand side is also equal. Then we have minus 4 pi square x upon t square is equal to minus kx upon m. Negative sign cancel by negative sign and x is cancelled out by x. Then 4 pi square upon t square is equal to k upon m. Taking the reciprocal on both sides, so t square is equal to 4 pi square m upon k. Now removing the square, then taking the square root on both sides, Now taking square root on both sides, t is equal to 2 pi m over k square root. This is called the time period t, that is time for the oscillation. So it takes for a mass spring system to complete one vibration. Now we have find the formula to find the time period, that is equal to t is equal to 2 pi m over k square root. Now we have know that where m is the mass in kg and k is the spring constant, its SI unit is Newton per meter of a spring system. It is worth nothing that the time period does not depend upon the amplitude of oscillation. So we can find the frequency of mass spring system, since frequency is the reciprocal of time period. Therefore the frequency of mass spring system is given by F is equal to 1 upon 2 pi k over m square root. Now for the factor it depends, so its factor depends upon the value of m and k. Then time period is depend upon the value of m and k. Now we have, it is clear that increasing in mass of body attached to the spring will be increase the time period and decrease its frequency. This means is that higher the masses will be complete a small number of oscillation in a specified time and compared to the lighter body and vice versa. On the other hand, changing the length of the spring will be no effect on the time period on frequency in a mass spring system. Now we will move the question number 3. Explain the following term for a simple harmonic motion: vibration, amplitude, time period and frequency. So we have known that now we will discuss the different terms which have the characteristics of simple harmonic motion. So first of all, vibration. So what is meant by vibration? One complete round trip of a body vibrating about its mean position is called one vibration. One complete round trip of an oscillating body during which it passes through all the points of its motion is called the oscillation or vibration or a cycle. One cycle is complete if a body starts motion from one point and reach back to the same point after passing through each point and every point its path, so it is called a vibration. Now what is meant by amplitude? The maximum displacement of vibrating body on either the side from its mean position is called its amplitude, or the maximum displacement from the mean position of a body performing the simple harmonic motion is called the amplitude. The maximum displacement from the mean position on the other side, it will call the amplitude, and amplitude is denoted by capital A or X naught, as amplitude is a displacement, so that is measured in a meter. Now we have seen by the time period. In time period we can see that the time period taken by a vibrating body to complete one vibration is called a time period, or the time period taken by a simple pendulum is complete in a one cycle, that is called a time period. It does depend upon the length of pendulum and independent of mass of and amplitude of pendulum. Now the frequency, what is meant by frequency? The number of vibration or a cycle of a vibrating body in a 1 second is called frequency. It is the reciprocal of time period. So F is equal to 1 upon T. Now in question number 4, explain a ball dropped from a edge of shining bowl performing a simple harmonic motion. See in this diagram. Here blue line shows body at a mean position. At a mean position, weight acting toward the downward and normal reaction toward the upward. So body at this point is a rest position. So it moves from O to P, P to O and O to Q. This motion is from its main position, so this performing a simple harmonic motion. Now we will discuss in detail vibration or oscillation occur about a mean position, also called the point of stable equilibrium. A equilibrium point is a point at which no net force is acting on a body. An equilibrium point is also called a stable point because no force is needed for two body to be there. At all other points and a small displacement from the mean point, the net force pushes the body back to the equilibrium point. This force is called a restoring force. Since it is tends to restore in equilibrium. Consider a ball at a equilibrium position in a bowl at a O point as shown in a figure above. When the ball is displaced from its equilibrium position, say to be a point P, upon releasing, it will be start moving under the restoring force toward equilibrium position, opposite to the displacement x. After reaching the equilibrium position O, the ball will be continue its motion under the force of inertia and will reach the other extreme position at a point Q, and thus it will be continue oscillate back and fro. Now the motion of the ball here is a example of simple harmonic motion. So which is the special kind of vibratory motion or also oscillatory motion, which occur whenever the restoring force F is proportional to the displacement d. From the equilibrium position, we can write mathematically F is directly proportional to minus x. Now, here the negative sign shows the restoring force and displacement are oppositely directed. So the restoring force try to decrease the displacement, then displacement is a point away from the mean position and the restoring force acting toward the mean position. Now the proportionality 1, equation 1 is shows for the restoring force lead us to the restoring acceleration. As for the force is always produce the acceleration. Recall the Newton's second law of motion. So according to the Newton's second law of motion, that is why simple harmonic motion can be defined as the type of motion in which the acceleration is directly proportional to its displacement, x from its equilibrium position. Mathematically, A is directly proportional to minus x. So, in question number 5, given statement according to the point is that what is the simple pendulum and shows that the vibrating body performing a simple harmonic motion of a pendulum, and what formula for the time period of simple pendulum on what factor affecting on it or depend upon it. Now, first of all, see in this diagram. This diagram shows the body in a simple harmonic motion, and this is the diagram of simple pendulum. Here we can see that L is the length of string, and where P is the point that have a mass M that move P to Q at a circular path. The distance is S. Body is moved toward the mean position due to the restoring force, and the perpendicular distance from the mean position to extreme position, this is called a displacement, that is denoted by x. Body moved toward the mean position due to the restoring force. This restoring force is mg sine theta, and other force is acting toward the outward and tension toward the string. Both are cancelled to each other. These force is a mg cos theta. Now we will discuss in detail. So move to the answer. In answer, simple harmonic motion. A simple pendulum is an idealized model consisting of a point of a mass m surrounded by a weightless less. In this thing is given and shows in this diagram. This is a very comfortable and fixed at a frictionless port. So here no friction between them. So explanation of a simple pendulum. A simple pendulum is drawn by the force of gravity due to the weight is pounded as a mass m. So W is equal to mg. Here we can see that mass in change into weight. So W is equal to mg. A real pendulum approximate a simple pendulum if they have the three conditions. The bob is small compared to the length L. Second condition, the mass of the string is much less than the mass of bob. And point 3, the cord or a string remain straight or does not stretch. So these three conditions are fulfilled by the simple pendulum. Now we have pull the pendulum of a bob aside and let it to go. The pendulum then swing back and fro, neglecting the air drag force and the friction of the pendulum at a pivot point, so the oscillation are periodic. We shall show that provide the angle is small angle theta. This motion is also in a simple harmonic oscillator, so we have the making triangle QRS. We resolve the weight W is equal to mg into two components, mg sin theta and mg cos theta. The component of mg cos theta is balance the tension T in a string. So the restoring force is only provided by the component of a force mg sin theta. Therefore, force F is equal to minus mg sine theta, and as also only for a small angle, arc length S is nearly the same length of the displacement x. So therefore, from the triangle OPQ, sin theta is equal to x over L. Putting the value of sin theta in above equation, then we have the force F is equal to minus mg sin x over L. Since m is the mass and acceleration due to the gravity of g and the length L are constant from a simple pendulum oscillating with a small angle. So we have write that force F is directly proportional to minus x mean its displacement, which is the condition of simple harmonic motion. Thus, the motion of simple pendulum can be approximate as the simple harmonic motion. Then, according to the Newton's second law of motion, F is equal to ma. Then, comparing the equation 3 and 4, ma is equal to minus mg sine x over L. Here m is cancelled out by m, then g and L are also constant, then the oscillation motion of pendulum A is directly proportional to minus x. So acceleration is directly proportional to its displacement, and negative sign shows that it is always directed toward the mean position. Then, according to both conditions, we release the mass, we will move toward the equilibrium position and will cross over due to the inertia and will execute the simple harmonic motion. Now, for a time period t simple pendulum, the acceleration and the displacement of a simple pendulum are related by the time period t by the following equation: A is equal to minus 4 pi x over t square. Now A is equal to minus g over Lx. So both equations, comparing the equation 5 and 6, then we get minus g over Lx is equal to minus 4 pi square x upon t square. Minus sign cancel out by negative sign and x cancel out by x, then g over L is equal to 4 pi square upon t. Now rearrange and taking the square root on both sides, we have t is equal to 2 pi L over g. The above equation shows that the time period of the simple pendulum, that is directly proportional to its length, and the pendulum is inversely proportional to its gravitational acceleration g. So the time period of the pendulum does not depend upon the mass of pendulum bob, or does not depend upon amplitude. So we have find the frequency f of a simple pendulum, since the frequency is the reciprocal of time period. Therefore, the frequency of simple pendulum f is equal to 1 upon 2 pi g over L square root. Best of luck in next remaining question in next video. Take care.